Okay, good morning, good afternoon, or good evening. It depends which part of the world you are in and, different places, different time zone. So anyway, today I will be talking on big data analytics. It's a joint talk with Faryal Ahmed. And as you see, I'm at the Brock University in Canada and my email address is there. So please, if you have any question, feel free to send me your questions via email, and I promise I will answer you in a timely fashion. Okay, and without any further ado, and as I mentioned, the part of the talks will be presented by Faryal Ahmed, and she happens to be my daughter too, so she is with me here. But she's at Ivy Business School, Western University, London, Ontario. So let's talk about the what do you mean by data and what's the things which we are doing nowadays and what data science is doing. It's pretty much, pattern recognition and then talking about some correlation and then in the prediction. So it's prediction, prediction, prediction. So how we do that? We have a data matrix N by P order. N is the number of the observation and P is number of predictors or features in computer science terminology. So it's N by P data matrix, and we have this N by P data matrix for a long time. The what what happens in the data matrix, I will tell you later. So we may have a response variable, if yes or no. So if it is yes, then we are talking about the regression model. If it is no, then we are talking about the ANOVA models. So let's come to the basic question. What is data science? What is big data? And what is high dimensional data? So in fact, data science was recognized as a field of science at the beginning of the century. So the volume of data, which is mostly people refer to big data, is due to the technological advancement, and the data can be stored now. So that's what we have a new things to deal with. But big data, we think, we have lots of information, we can do some better things. To me, it may create big problems, not in all cases. And the information may not be valuable. So seems like a paradox. Paradox, it means two reverse conclusion may hold. So data needs to be basically extracted to make the data valuable for future study. So we are doing it with some people call it data mining, data cleaning, massaging, interrogating the data, or even torching to the data so we can get our whatever we are looking for. So basically, either we are doing, if it is a big data in terms of volume, we are doing data reduction, or we are doing variable selection, or both. So data reduction, I mean, in statistics, we have a sufficiency principle which used for the data reduction, and also we have a PCA which can be used to variables reduction or predictor reduction. I mean, when I talk about variables or feature reduction in N by P data matrix. So we have been doing it for long time, for decades, for many decades. But this situation is different now. We have large N and we have also large P. So how to deal with that thing? So the bottom line is it's a data reduction, extracting the valuable information from a big data. In fact, it's called the data science. In my perspective, in my view, that's what data science is, the studying the big data or high dimensional data. So once again, big data matrix, N by P. So what's the situation? That in one situation, N can be very large. So it is, we are talking the volume of the data, lots of observation, satellite data coming every microsecond. In your cell phone data is providing you lots of data. So due to data volume applications, some of the classical methods may not be feasible or may not work. So in second situation, and maybe moderate or even small, but the P can be very large. So maybe say N is 100 and P can be 1,000,000. It's hard to believe that P can be that large, but I will give you one example later on. And then in high dimensional data, situation is much different. People use the word ultra high dimensional. I don't believe in inventing too many jargons. So N is very small as compared to P. And then there is a situation both N and P can be large, and even we can make it further complicated that N increases as P increases, or P increases as N increases. So as we all know, it's pretty much 20 years old stuff now. There are four V issues: velocity, speed of data processing. Speed of data processing can be very challenging when the data is coming through satellite and or even stock market data. Every second data is changing. So how to process this? And the volume is the amount of data, huge volume, and then we are doing some intensely, volume is coming, and then we have to process it. And then variety, and now this data is just not like a number, like N by P matrix. It could be various type of data. But for us, a statistician, veracity, which means the uncertainty and imprecision in the data, which is more important. So as I said earlier, big data doesn't mean the big value. It could be more trouble if the data is not precise. So, there are describe the situation, the volume, variety, and velocity of data may exceed an organization's storage or computer capacity. So there is not a number like 1,000,000 is big data or 1 billion is a big data. If it exceeds your capacity, even on your laptop, to me, it's a big data for you. And then in terms of the variety, we may have a pictures, audios, video, text, emails, etc. And Faryal will analyze the data and give you the one example how the text can be used in analyzing the data. So we all know that big data or high dimension data is very important, lots of application and lots of jobs. People are, it's a new title of data scientist instead of chief economist. This is taking place at many organizations. So then Faryal has just talked about you the learning part.
And today I'll be talking about machine learning and some classification models along with a case study. So to start off, let's talk about learning. So learning in computer science is a branch of artificial intelligence concerned with the design and development of algorithms that allow computers to evolve behaviors based on empirical data. So as our brain requires knowledge, so do computers in order to learn. So the type of algorithm is what dictates the success of a machine learning system. There are two main classes of algorithms, supervised and unsupervised learning. Things that you may have already encountered are usually supervised learning, meaning you want to either predict something or classify with a logistic or multinomial regression. The differentiating factor is that you have your data labels and you know what you're looking for. In contrast, we have unsupervised learning, which is when sometimes all you have is a lot of data and you can't make any assumptions about what influences what, and in some cases or labels are left undefined. For example, survey data or medical data can be multidimensional and hard to interpret. So we're left to do some clustering or dimension reduction, but all we have is like a cluster ID or a representation, or in comparison to supervised learning, we have an expected value or label. So when constructing models, we always want the most parsimonious model. Can we explain the data with the least possible amount of variables without loss of generality? In supervised learning, we would represent these variables in some sort of regression. By doing so, we inherently make some assumptions, like using a correlation cutoff value of 0.4, or using regularization techniques like lasso or ridge regression to reduce the variables based on a penalty function. that also requires cross-validation for tuning parameters, unsupervised techniques, look at how the data is naturally being grouped based on where the data points are in a multidimensional space, eliminating such assumptions. So for today's case study, I'll mostly be covering supervised techniques and in particular classification techniques. So there's a lot of classification models that are available, and some of them are hard to interpret, some of them are easier to interpret, some of them have more of a lower computational cost, but today we'll be going through some of them. So to start off, we'll talk about MARS, Multi-Adaptive Regression Splines. Introduced by Friedman in 1991, MARS constructs piecewise logistic regression to capture nonlinearities, and these splines are constructed from a set of coefficients and basis functions driven from the data. So it's particularly become popular in the area of data mining because it does not assume or impose any particular class of relationship between the predictor variables and the dependent variable of interest. In a sense, the method is based on a divide and conquer strategy, which partitions the input space into regions, each with its own regression equation. After fitting, it computes a predicted continuous values or scores. Finally, for prediction, it assigns each case to the class for which the highest score is predicted. Note that this type of class application will yield heuristic classifications that may work well in practice, but it's not based on any statistical model for deriving classification probabilities, and it can be prone to overfitting. In KNN, we have K nearest neighbors. So in KNN, it stores all available cases and classifies new cases based on a similarity measure. So these are through distance functions. And KNN has been used in statistical estimation in the 1970s as a non-parametric technique. So in KNN, K is the number of nearest neighbors. The number of neighbors is the core deciding factor. First, you find the K closest point to P1 and then classify points by majority vote of its K neighbors. Each object votes for their class, and with the class that with the most votes is taken as the prediction. For finding close to similar points, you find the distance between the points using the distance measures such as Euclidean distance, Hamming distance, Manhattan distance, and Minkowski distance. And then we have some a collection of decision trees, which makes up a random forest. So it's an ensemble of decision trees that returns a class prediction, and via a ranking algorithm, the class prediction with the highest votes is the model's prediction. And next we have support vector machine. So SVM was derived for the classification with K equals 2 classes. So when their 2 classes are separable, the maximal separating decision boundary is a hyperplane that can be found using quadratic programming. Basically, you want to maximize the distance between 2 classifications, and as long as the separation is well, you're able to classify each point into each side of the hyperplane. Then we have linear discriminant analysis. So this is what it models a distribution of predictors separately in each of the response classes. It maximizes the component axes and then uses Bayes' theorem to estimate the probability. And the last 2 are a little bit more difficult machine learning algorithm techniques to understand because they learn from a training set to give a prediction. The neural network is designed after our own brain's neural pathways to recognize patterns. An artificial neural network is a system, and this system is a structure which receives an input, processes the data, and provides an output. So the input is presented to the neural network, and its required target response is set at the output. And every time the neural network learns, there's an error obtained. The error information is fed back into the system and makes any adjustments to their parameters in a systematic order, which is commonly known as the learning rule, and it's repeated until the desired output is accepted. Lastly, we have gradient boosting machine. So it repetitively leverages the patterns in residuals and strengthens a model with weak predictions and improves it. Once the residuals do not have any pattern that could be modeled, we stop. Algorithmically, we're minimizing our loss function such that test loss reaches its minima. So a gradient boosting machine is just an ensemble of different machine learning techniques. And an ensemble is just a collection of predictors which come together using the mean of all predictions, for example, to give a final prediction. This technique employs the logic in which subsequent predictors can learn from the mistakes of their previous predictors. Therefore, the observations have an unequal probability of appearing in subsequent models, and ones with the highest error appear the most. So the observations are not chosen based on the bootstrap process, but based on the error. These predictors can be chosen from a range of models like decision trees, regressors, or classifiers. And then computing the gradients of the loss function, we want to optimize for each output object. And the learning just predicts the gradients of the loss functions. So what we want to know and what we want to compare is which performs the best and which is the best algorithm for your case or for whatever case study you're trying to achieve. So there's lots of different types of definitions of machine learning. There's a paper, Samuel coined the term machine learning for checkers game later in Jeopardy. There's another one where a computer program is said to be learning from experience E with respect to some class of T, according to Mitchell in 1997. And there's plenty of examples of machine and statistical learning techniques, such as autonomous cars, fraud detection, and the field of machine learning originates from computer science, mostly from that artificial intelligence and statistics. So as mentioned before, we have supervised learning and unsupervised learning. And we also have weakly supervised learning when sometimes we have control over an unsupervised case. For example, k-means clustering is weakly supervised because you choose the amount of clusters. And again, we have lots of different techniques such as random forest and CART and boosting, stacking neural networks. But in machine and statistical learning, labeling is referred to fitting or estimating a function. Features can be described as predictors or explanatory variables. Features is more of a computer science term. Overfitting and underfitting are a lot of computer science term. Overfitting regarding to a full model or unrestricted model, and underfitting regarding to a submodel or a reduced model. And as mentioned before, there are a lot of regularization techniques for penalty estimation to avoid this overfitting problem by applying additional constraints to the models. There's lots of different penalty functions that can be used, AIC, BIC, L1 and L2 regularization. L1 is lasso, where there's a penalty term forces the sum of absolute values of regression parameters to be small or zero. L2 ridge is a penalty term for forces the sum of the squares of regression parameters to be small. So L1 produces variable selection where ridge regression does not. So when we're talking about big data and streaming data, N is very large. Streaming data is commonly encountered in several different businesses and industrial applications, leading to the so-called big data. Big data and streaming data are encountered in a variety of contemporary applications in business and industry. The data is continuously generated by different sources, and we get real-time data. So this data streaming is a process of sending data records continuously rather than in batches. And streaming is used to examine continuous data streams and quick detection with a small time period after receiving the data. So when we're combining different health data banks with a great heterogeneity collected over time, the problem with big data is that it's not homogeneous, it's heterogeneous. So Facebook has more than 950 million users and they spend approximately 7 hours on average for a given month. So this is a huge task to store and analyze such big and complex data, as well as in financial analytics. Credit card companies need to target for cardholders, focusing on customer default payments. And this data can be consisting of extremely heterogeneous variables. So when we're talking about high dimensional data, one example is in genomics. In genetic micro studies, N is measured in hundreds. The number of features per sample can exceed millions, and 22,500 unique proteins implies about 253 million possible protein-protein interactions. And only so far, 42,000 of them have been identified. So we need some kind of predictive engine for this. So in high-dimensional data genomics research, it's an interdisciplinary field of biology focused on the structure, function, evolution, mapping, and editing of genomes. And a genome is an organism's complete set of DNA, including all of its genes. Genomics is an area within genetics that concerns the sequencing and analysis of organisms' genome. The genome is the entire DNA content that is present within one cell of an organism. Experts in genomics strive to determine complete DNA sequences and perform genetic mapping to help understand diseases. So in this case study, we're talking about what is the motivation behind genomics. For example, accessible databases like ClinVar have become a saving grace for many researchers. Free public archives such as ClinVar provide reports on the relationships among human genetic variants and phenotypic expressions with supporting evidence. The ClinVar database provides researchers with the means to theorize relationships such as variants and observed health status. More specifically, the database has nucleotide, mutation, and gene location information with regards to the evidence and variation of the condition information from studies and tests made, and finally the interpretation that leads to a diagnosis based on the aforementioned, in particular in form of the ACMG score. The ACMG has a recommended 5-tier classification system. According to this system, a sequence can change between benign and pathogenic. So the problem here is where the ACMG classifications, the level of confidence in the accuracy of claims of clinical significance are reliant on the supporting evidence and origin of the report submissions, meaning that genetic variants are manually classified by clinical laboratories on a categorical range. These variants can be classified as benign, likely benign, indeterminate, likely pathogenic, and pathogenic. From laboratory to laboratory, variant misclassification causes uncertainty in the interpretation of variant impact on disease. So this VUS stands for variant of uncertain significance. So their level of confidence leads to some uncertainty in the accuracy of the claims of clinical significance. And these are just reliant on these doctor reports, but they can be conflicting when it comes to 2 different labs and 2 different patients. So a comprehensive ClinVar dataset was uploaded on Kaggle for the public to explore data analytics, application, and genomics. The data is comprised of 65,118 observation and 46 variables, to which one is a binary target variable. Variant classification conflict, class is equal to 1, or concordant class is equal to 0. The data defines conflicting classification when 2 of the 5 categories are present for 1. The predictors describe exhaustive genetic information such as chromosome, alleles, and axon information relative to the impact of disease, and up to laboratory notes where the data on the patients is collected. So using the topics introduced beforehand, addition to some popular machine learning applications, will investigate which ClinVar human genetic variant features or combinations thereof will help researchers predict classification conflicts with the most suitable model. This is a binary classification problem, and with so many options out there for prediction, we will explore some of the hot topic machine learning techniques that sound more like buzzwords these days and evaluate their predictive power. Since the data has 46 attributes comprised of continuous, categorical, and text features, it creates a complexity and task of visualization and exploratory analysis very formidable. But just to give everyone an idea of what type of information we're dealing with, let's see how the target variable is distributed by gene. There's an obvious class imbalance problem to which the data will be balanced by undersampling and oversampling, such that the minority class classification conflict is oversampled with replacement and majority class classification concordant is undersampled without replacement. But this simple frequency chart shows us how critical it is to understand clinical data and build appropriate models. For instance, TTN, the gene that encodes a large protein called titin of striated muscles, and BRCA2, the genes that provides the instructions for making a tumor suppressant protein, both of which are imperative to our cellular health, and conflicting variants can be detrimental in diagnoses. With 40 plus features that have several categorical variables need to be accounted for with an indicator variable in each of the model, it can be very computationally taxing. Those who understand their own data or possibly collected it will be able to perform some sort of dimensionality reduction by inspection or employ other methods. However, dimensionality reduction without knowing how your data behaves can limit your analysis, especially in the case where your genomic data is so complex it's difficult to tell by inspection which predictors are important. This is where some unsupervised learning can help find the natural tendencies in the data. So for instance, one feature that is difficult to analyze and draw conclusions from are the texts manually entered by the laboratory that it reports the notes on diseases with respect to classification conflicts. Here's a chance to implement some unsupervised text mining. These laboratory notes come from professional doctors and oftentimes variables that contain strings that are often dropped, but open-ended descriptions by patients or the lab describing system might yield useful clues for the medical diagnosis that go unnoticed. This word cloud generated below shows the most common clinical words describing diagnoses that are associated with classification conflicts as it reports the top words from laboratory reports. These top words could potentially aid in prediction of whether or not a classification could conflict. Using these top 5 words frequent in conflicts, a new variable is created called potential. This feature is engineered by filtering each observation's laboratory reports note string by the top words found. This is how autocomplete works on one's phone function based on the frequency of association. So then we have to prepare the data, obviously. Is there multicollinearity? Are there missing values? And then what method to use? So what we're going to do, we're going to employ all the methods that we talked about beforehand: lasso, Mars, KNN, random forest, neural net, LDA, support vector machine, and gradient boosting machine. But before that, we want to do some variable reduction. So we employ L1 regularization, a logistic regression with lasso. So we use lasso and we cross-validate, and we find that there's 13 significant predictors to predict variant classification conflict. And here's just the top 5 significant predictors in this data. And we can construct a new submodel. And just to give everybody a brief overview of what the model descriptions are, the pros and cons, and the optimal method and optimal parameters for each Mars, KNN, random forest, SVM, LDA, neural net, and GBM. And let's look at the results. So we can tell that the misclassification rate varies. But what we're seeing here is that lasso and logistic regression easily competes with these sophisticated machine learning techniques. So we have lasso and logistic has high interpretability and low computational expense. Meanwhile, even though gradient boosting classification has the best and lowest misclassification rate, it has poor interpretability because it's just minimizing error from the inputs, and it's a high computational expense. So what we're seeing here is that once we control for bias and we have a submodel, statistics and machine learning do not compete with each other. They simply complement one another. And I'll hand it off to Dr. Ahmed to talk more about supervised learning.
Okay, so now it is my turn again. So thanks Faryal for your interesting data analysis and the review of a machine learning techniques. Now I'm going to put the mud on the water. So all these machine learning techniques, they are subject to bias. We all know that. So to begin the process and see how we can control some of the bias, let's start with a multiple regression model. It's a usual classical regression model. The only difference is that it can accommodate when P is much larger than N. So what we do, we suppose that we talk about the sparsity, because there we may have a large data matrix with millions of predictors, but there are few are important. So if we can partition the parameter vector space into beta 1 and beta 2, and we assume that model is sparse, that beta 2 is a null vector, and beta 1 is the important parameter vector with dimension p1, and p1 is less than n, and of course the p2 is greater than n. So we do a variable selection techniques to get the model only with beta 1. We say submodel, and the parameter of interest is beta 1. So we would like to do the estimation of beta 1. To me, it's a post estimation. First, we select the model, and then we do the post estimation. So here is the generally penalized likelihood techniques. You can see, you can recognize this part, and which is a likelihood or least square function. In penalized likelihood, we add a penalty function, which take this part. And we have been using it, the ridge regression, for some time, which is in fact a special case of penalized likelihood for gamma equal to 2. So it's a square penalty, or we call L2 penalty. And this can also take care of the situation when P is greater than N. So the important work is in this area is the L1 penalty, which is called lasso. So you can see this is the L1 penalty. So with this penalty, it's a diamond shape, so it can force weak coefficients towards 0. So and it does two things together: select some model and do the estimation of regression coefficient. And it has some connection to Bayesian methods. So penalized likelihood methods give you some model and estimate the parameters, and then you go do the prediction error. So is it the end of the story? Not really. Let us dig in deeper. So the penalized methods, or any machine learning methods, if it's a good strategy, if the model is truly sparse. So otherwise, we will have a problem with underfitted model or some model. Some model estimates are usually biased. We know it, and bias is the biggest problem in the big data. So we need to control the bias. So let's look at this slide to see how the bias comes into the picture. So suppose, we can partition beta 1, beta 2, we can partition the data matrix into x1, x2, and then look at the bias, calculate the bias. But keep in mind, our parameter vector of interest is the beta 1. So we are taking expectation with respect to beta 1 hat. So you see it has a beta 2 right there hanging. So unless beta 2 is 0 or null vector, we will have a bias. So the MSC will increase with bias increases. And actually it will explode. There is no bound because bias is keep increasing. So this is not a good trade-off to just only work with the submodel. So I paraphrase GEP box. All submodels are biased, but some are useful. So it is important to understand the impact of the bias when you are doing a prediction or you are doing a model parameter estimation. So without some statistical understanding, people cannot understand. So you need to understand what's bias is and how it's play the roles mathematically. A naive data analyst or data scientist, whatever we call it, will not comprehend that dropping x2 from the model, the impact will be large. So unfortunately, the law of unconsciousness may not work in this case. So we need to control the bias. So there are many penalty estimators are available in the literature and people are using it. And then as I say, the sparsity in the model that most coefficients are exactly 0, few are not. And non-zero coefficients are big enough to be separated from the 0 one. These are very strong assumptions and may not hold in all cases. So the problem is you have a full model, you have a sum model. So in full model, or you have too many predictors. In some model, you selected a few predictors, and then you are subject to bias. So there is a issue of model interpretation, prediction accuracy, and how to deal with the bias. Because we are completely ignoring the weak signal. So in this talk, I would like to talk about, let's consider weak signals in building the model. So once you have a full model with many predictors, one you have a some model with few predictors, why not combine these two? So how to combine them? So for combining, so we are talking about the post selection strategy. You use a penalized likelihood methods or AIC, BIC, or any other criteria to get a sum model, and first, and then construct a shrinkage estimator. But shrinkage estimator is there for 4 decades, but mostly for fixed P, and N is larger than P. So we have to extend that work. So what we say, if we can have instead of just strong signals and no signal, let's incorporate weak signal. So S1 is strong effect, S2 with the joint weak effects, and S3 no effect. So basically there are some, of course, regularity conditions. So basically we can get it, strong effect, through any penalized likelihood technique, and let's call it restricted estimator based on S1 subset, the usual estimators. And we have recorded this work in this paper, which was a discussion paper. So step one, we get these strong signals, and next step, we try to get from the weak signals, joint weak signals. So which is done by using the weighted ridge regression. So we can get some coefficients of the with weak signals by using this estimator, beta hat weighted ridge. And then we will combine ridge estimator. We can think as a estimator based on the full model or with many more predictors as compared to beta hat RE, and we put them together, and here we get the shrinkage estimator. So it is a function of RE, function of weighted ridge, and through a distance measure T hat. And so you can see, if this quantity goes to infinity, we are back to some model estimator, but this is for the small values, it will play an important role. It will shrink weighted ridge estimators toward the restricted estimator. So all the other terms are defined here, and we can take a positive part to avoid the over shrinking problem, which is inherited in the construction of shrinkage estimator. And now, after constructing all this estimator, we can calculate the asymptotic properties. So we call it mathematical and creative proof. So we can calculate the asymptotic distribution risk. So you can see weighted ridge is standardized at 1. And then if this delta means if delta equal to 0, it means selected some model is correct one. So you will get a small value, smaller than ridge estimator, and then we can also calculate for SC and PSC, proposed estimator. These are our beautiful expressions. So, and in fact, if you trust me, I can tell you if this delta goes larger, it will be the ADR will be close to 1 or less than 1. So we beat the full model estimator and we control the bias. So let me show you some numerical work, because creativity is subjective and truth is not. So let's look at the relative mean square error, which is the MSE of weighted ridge divided by MSE of any proposed estimator or used estimator. So for simulation studies, we call it engineering or artistic proof, because like an artist, you can select your parameters, or you can select your colors or parameters as you wish. So it has both strong coefficients and the weak coefficient, and of course the sparsity. So here is the results. So this is the submodel estimator, this is proposed shrinkage estimator, positive part, and this is the penalized likelihood, SCAD, MCP, A lasso, and lasso. So you can see for P1, 3 strong signals, and then this P is P1 plus P2. For large P2, and then it's mean there are more weak signals, you can see the impact of the performance of PC is pretty good. And the performance of all the penalized methods are not as good as PCE. And especially in the case of, say, P1 is 10 and then P is 456, when the weak coefficients are increasing, it's PSC is doing as good as some model estimator, but look at the penalized likelihood, lasso, MCP, other, they are doing worst. So now I give you an application. This data was analyzed by Huang, Ma, and Zhuang in 2008. And so almost 19,000 predictors. And the Huang et al., they found 19 and 24 props based on lasso and adaptive lasso. So we use this as a restricted estimator, and then we also do the weighted ridge and then compare with the lasso. So we calculate the relative prediction error and look at this error in this box plots. The first two box are based on lasso, the other two are based on proposed estimator of shrinkage. So you can see the prediction error is very small. It's a genomics data, and you can see the genomics data, there are lots of weak coefficients. So due to weak coefficients, the prediction error is very large for lasso, and it's very small for our proposed methods. So it corroborates the theory and the simulation results. And so when there is a weak coefficient, you cannot ignore it. It will create bias, as shown with these two lasso box plots. So we have generalized into the shrinkage estimation for high dimensional data, and it works very well. Here are some of the references. We have keep doing work and trying to further improve by using weak signals. And we have published many papers in different areas. And also I have a book in 2014. And then through this workshop on high dimensional, we have done some special edited volume, special issues. So the work is going on. So seems like to me is a clash of cultures between statistical science and data science. We work with pre-processed sample data, exact analytic solution, low dimensional data analysis, SAS, SPSS, idealistic work alone or in a small team, and the glory of the individual. But however, big data available from different sources, we need to frame the problem, identify the data for analysis. Is it a population or sample data? People have no idea when they present their work, and when I ask them, are you analyzing a population data or sample data? They get lost. So we have to make sure. So new tools for new data, Python, R, open source program, parallel cloud computing, Hadoop, Sparks, and other, visualizing complex data, and combining data is the very important area. We call it data fusion, the code linkage, for example, tax returns, court records, and healthcare agency. So it's a lots of bias can come into record linkage if it's not done properly. So far in data science, we have been doing the pattern recognition, correlation, and the and the prediction. But now we have to take it to next level. There is lots of work need to be done in high dimension data analysis. We need to be pragmatic, think tanks, transdisciplinary research, glory of the research team. So I would like to take this moment to thank you to the organizer for putting this conference together. I have been helping them, but it's mostly the local organization did all the great work. And almost, or more importantly, thank you to all of you for sharing your valuable time with me. Thank you.